Thank you for joining us tonight for After Dark Online, The Universe. My name is Kathleen McGuire, and I'm part of the team that puts on these weekly After Dark Online programs. While tonight's program has been recorded remotely, I want to acknowledge that the home of After Dark, the Exploratorium at Pier 15 in San Francisco, is located on unceded territory traditionally belonging to the Ramaytush Ohlone people. We recognize we are guests on this land and honor the elders from past, present, and future for their caretaking and shepherding of the land. Earlier today, the Exploratorium collaborated with NASA to share and celebrate Landing Day for the newest Mars rover, Perseverance. You can find that program, as well as many other programs that look at earlier Mars rover missions on our website and YouTube if you're interested in digging in further. For tonight's After Dark, we thought we'd stick to the space theme, but look a little bit beyond Mars to the entire universe. Also throughout February, we are honoring Black History Month by sharing underrepresented histories from Black communities and cutting-edge work from Black scientists, historians, artists, and thinkers. Tonight, we're thrilled to be joined by two Black scientists whose work and research is at the forefront of our ever-expanding understanding of the origins of the universe. Later on, we'll be hearing from theoretical physicist Dr. Chanda Prescod-Weinstein on her research into dark matter and how theoretical physicists approach this work. Up first, Dr. Gregory Mosby Jr. with his talk titled Catching Light, How Astronomy Reveals Our Origins and Destinations. Dr. Gregory Mosby Jr. is an extragalactic astronomer interested in galaxy evolution studies and building new instrumentation to further those studies. He is currently a research astrophysicist at NASA Goddard Space Flight Center, where one of his primary projects is the development of the Nancy Grace Roman Space Telescope, which he'll be sharing a bit about in this talk. Greg grew up in Memphis, Tennessee, before heading to Yale University, where he graduated in 2009 with a bachelor's in science in astronomy and physics. He then headed to the University of Madison, Wisconsin to complete his doctoral work. His current research interests include near-infrared detectors, astronomical instrumentation, and the applications of machine learning to observational astronomy. Here's Greg.
Thanks for that introduction. I'm so glad to be here with you all this evening as part of the After Dark Online program. And I'm really excited to talk to you about something that I find really fascinating, which is how astronomy can reveal our origins and our destinations. And the way astronomy does this is it's all about catching light. And I'll talk to you about that throughout this presentation. Now, you may have noticed this really pretty picture I have in the background. But this pretty picture, which is kind of a simulated image for a new telescope that I'll talk about later, is more than a pretty image. It's actually from the Andromeda Galaxy. And Andromeda is pretty special. The Andromeda Galaxy is actually our nearest neighbor. And nearest neighbor may not mean a lot now, but when I start talking about the scales, it'll make a lot more sense. Andromeda is about 2.5 million light years away. And that's very, very far. But in terms of the universe, it's actually very close. If you were to try to weigh the galaxy of Andromeda, weigh all of its mass, it would be 1.5 trillion times more massive than our own sun. And our sun is quite heavy. Another really cool thing that may also be a little frightening, but there's no need to worry, is that Andromeda is actually on a collision course with our galaxy, the Milky Way galaxy. But that's not due to happen for another 2 billion years, so there's nothing to worry about here. These are all really fascinating facts about an Andromeda galaxy. You may wonder, well, how do we know all of these details about this object that's so far away and that we can see in the night sky? Well, the answer is we know all of this because of the light that we get. Light is how astronomers study the universe. If you think about how other scientists study the universe or study their particular fields, you usually think of them having a laboratory and having tools and instruments. Well, in astronomy, the laboratory that we use is the universe. The universe is where we get all of our observations from. And how we learn about the universe is with these tools of the trade that are telescopes. And by attaching instruments to these telescopes, we learn even more details about how the universe is evolving, how it's changing, and what it may become. Now, these telescopes, we like to use this analogy a lot of times in astronomy. The telescope is like a big light bucket. It allows us to collect the light and to focus the light. What's really cool nowadays, though, is that now we can focus the light, and digitally record it onto sensors. These sensors are like the detectors that you have in maybe your cell phone camera or in your laptop camera that allow us to actually digitally record the signals we get from the sky, save them, and then go back into our laboratories or into our offices and actually analyze the data and learn about the universe. In older times in astronomy, they actually had to use photographic plates to record these signals. So as things have progressed in technology for our era, our way of doing science has also progressed. Now, we talk about light. We can get light from lots of different sources in the universe, but the light we get from stars is particularly special. And not just because, hey, the light we get from the sun, which is our star, is essential for life. The light we get from stars can also tell us a lot of detailed information. On the left here, I have an image of our sun taken through a telescope and recorded on one of my digital cameras. On the right, I have what we call a spectrum. This is where we take the light from an object and we put it through a prism or a dispersing element to spread out the light into all these constituent different colors. And what you see plotted here is that spectrum that shows the intensity of light of all these different colors that we can find coming from our sun. This spectrum is extremely dense in information and is why we can learn a lot by looking at starlight. A lot of that we can learn about stars is explained in what this diagram on the left is showing, which is the Hertzsprung-Russell diagram. This diagram shows that what we know about stars all comes down to the star's light, and that there's this neat sequence that ties it all together. In this diagram, we think about a population of stars. We know stars form from these clouds of molecular gas, and they typically form a population of stars that are distributed across a bunch of different masses. Well, when you take the stars from a birth cloud, a population, and you organize them in this way, where you put the brightest stars toward the top of the plot, and you put the bluer stars to the left and the redder stars to the right, you get this really neat diagonal sequence that we call the main sequence. And what astronomers found out is that this sequence is actually a sequence in mass. It turns out that if you look at this diagram, the brightest and bluer objects tend to be the more massive stars, the larger stars. And when you look at the bottom right, the dimmer stars that are less bright tend to be the redder stars, and those stars tend to have less mass. So by looking at the light from a star, we can tell its mass, we can tell the age of the star, and depending on the chemical elements that went into that birth cloud, we can also place that star in this diagram and learn information about the universe at that time the star was born. Now, because we can learn so much about a star's history, a star's origin, we can also learn a lot when we think about how that population of stars changes with time or ages with time. We have the same diagram on this plot, but we can think about what happens if this population of stars we're showing here got older. Well, what happens is that these more massive and bluer stars actually go away. These massive stars tend to explode in supernovae very soon after those stars are born. So if you're looking at a population of stars, the stars in this bluest high mass area tend to go away. So you lose the light from those stars in your population. And you tend to retain the light from these dimmer and redder stars. So as a population of stars ages, it tends to get redder and dimmer. And we can actually use this fact to study large ensembles of stars, which are galaxies. Now, galaxies are these large, gravitationally bound ensemble of stars. And galaxies are really where all the action happens in the universe. They're where all of the baryonic matter in the universe resides. And the baryonic matter, I mean, that's you and me. Galaxies are like the factories of the universe. They're where the gas collects and then forms those stars that I talked about. And it's where these stars, especially those massive ones, explode as supernovae and return these higher atomic number elements back to the universe. Those are the elements that you and me get made out of eventually. So knowing the history of galaxies and understanding their fate is knowing our history and understanding our fate. So studying galaxies is a really important part about looking at our origins and our destinations with astronomy. Now, I study how galaxies change with time, particularly galaxies that have these active black holes in the center. So I'm showing a movie here that shows a simulation on how we think galaxies form. We mostly think galaxies form by having smaller galaxies collide and merge into larger galaxies. We call this hierarchical merging. On the left here, you see what the starlight from these galaxies in the simulation looks like. And on the right, you see what the gas temperature is in these galaxies. And what I want you to notice is, as these mergers happen to form this larger galaxy, you'll start to see the cooler gas, which is blue, get ejected out in these little bursts, almost like firecrackers going off. This is where accretion onto a black hole in the centers of these galaxies is ejecting large amounts of gas from that galaxy. By ejecting large amounts of gas from the galaxy, a black hole in the center can really affect the growth history of a galaxy and affect how large that galaxy eventually grows to be. By getting rid of the gas in the galaxy, you essentially shut off the star formation, because star formation needs gas. It needs cool gas to be able to form. And so as you see these firecrackers go off, we're thinking about how a black hole is impacting the environment of the galaxy. On the left, what happens is we're left with this large, big conglomeration of stars. They're mostly redder stars because there's no active star formation anymore, because we've gotten rid of the gas that could form stars. Now, this is really exciting work, and we really want to figure out, well, is this model correct? The way we figure out if this model is correct is we have to go and try to observe some of these galaxies. Now, when we want to observe these galaxies, we are using the same principles that we talked about earlier with the stars and looking at their light and figuring out their ages. By looking at the ages of the stars in the galaxy, we can try to track back and figure out the population growth, the growth of the galaxy. And we can tie that to what we see going on with a galaxy's black hole. Now, the analogy here in doing this growth history analysis is that it's like taking a snapshot of a picture of everyone here on Earth and then trying to sort everybody into different age bands based on their age. And then looking on a plot at how many people were born at a particular age, and then kind of extrapolating that, well, at that particular age, there must have been a boom in the population. For example, if 150 million people that you count in this picture are 33 years old, you would surmise that 33 years ago, 150 million people were born. We do the same thing with starlight. We try to figure out the star's birth rate and the galaxy's growth rate based on how many stars we see at a particular age. Now, this can be quite hard, not only because these galaxies are typically farther away, but if you want to study galaxies where the black hole in the center is actively accreting material, you actually have a very hard time. On this image here, I'm showing you the quasar 3C273. Quasar is just a word we use for a galaxy that has an active black hole. You see on the left, in this picture from the Hubble Space Telescope, that the image looks like a star. You can't tell that there's a galaxy there. However, on the right, they used a coronagraph instrument on Hubble to occult the center of the galaxy with a small disk. And what you see is that now there's this fuzzy bit right around the center of the galaxy. That's the galaxy. So when we want to study what's happening with galaxies where the black hole is actively accreting material, it's a quasar, we have to try to study these fuzzy bits. And studying these fuzzy bits is not all that easy. We know, I showing you here on the left, that this quasar in the center can outshine the whole galaxy. And when we try to avoid it, let's say we try not to look at the galaxy light at the very center because we know the quasar is there. We try to look a little bit off the center. You know, the physics of the universe essentially works against us. It turns out in galaxies, the density of stars tends to decrease quite rapidly as you move away from the center of the galaxy. So when we look off of the center of galaxies, we're actually probing fewer stars. So we get fewer light. So it makes our job of catching the light from these objects with our telescopes and analyzing it a lot harder. Well, it turns out machine learning, which you guys may be familiar with or have heard in the news, can actually help us out with this. Now, machine learning is just this method of trying to extract features in your data and then take advantage of those features to do some new type of analysis, whether it's clustering objects together and grouping them, or classifying or making predictions. This diagram here just shows kind of the two branches that machine learning splits off into. There's unsupervised learning, where you're mostly interested in grouping things that results in clustering objects. And then there's supervised learning, where you're interested in developing a prediction from your data. Astronomers use both types of machine learning in our everyday work. I particularly use machine learning to simplify the measurement of the gross histories of galaxies. You'll recall that I said we have to kind of sort the light that we get from galaxies into a bunch of different ages. I use machine learning to simplify that to only have to decompose and sort out the light into a few broad age bands that machine learning helps me select. By selecting those few age bands, I'm able to actually look at the light from a galaxy, fit the light from a galaxy, and make predictions about the growth history of that galaxy. And a lot of my research has shown that using that method is very precise and just as accurate as methods as scientists use currently. Other scientists use machine learning for other things. One example is looking at the galaxy's shape, or what we call morphology. And I have a picture here of the Edwin Hubble classification scheme. People are using machine learning to take images and predict or figure out and classify how a galaxy looks based on the shape in the image. There are even scientists that are using machine learning algorithms to go and search for exoplanets. Exoplanets are these planets around other stars outside of our solar system. So machine learning has lots of applicability to astronomy, and the automation that comes with machine learning will allow us to study lots of galaxies. Now you don't have to have a human involved. You can train a machine to do these sorts of tasks. Now, when you can train a machine to do these sorts of tasks, it allows the studying of large amounts of galaxies, and large amounts of galaxies allow us to learn about our universe. One thing we learned about our universe in the last few decades is that not only is our universe expanding, but it is accelerating in this expansion. We call the driving force behind this acceleration dark energy. And we don't know much about dark energy, but scientists are working to figure out what is dark energy. This discovery was only made possible by looking at the signatures of exploding stars throughout our universe. And by looking at thousands of these exploding stars, scientists were able to map out how the universe was expanding and to see that it was unexpectedly accelerating. Well, to really nail down dark energy and to really understand our universe, we need to study millions of galaxies. And the upcoming Nancy Grace Roman Space Telescope is going to allow us to study millions of galaxies to do just this type of work. Now, the Nancy Grace Roman Space Telescope is named after Dr. Nancy Grace Roman. Dr. Roman was a pioneer at NASA who was key in the success of the Hubble Space Telescope. She received her PhD in 1949 from the University of Chicago. She also worked at the Naval Research Laboratory. And in 1959, she became the first woman who was an executive at NASA, holding the position of Chief Astronomy and the Chief of Astronomy and Solar Physics. And because she was so instrumental in making sure that the Hubble Space Telescope got launched, people often refer to her as the mother of Hubble. So it's only fitting that now part of Dr. Roman's legacy will be this state-of-the-art telescope that is going to be exploring through surveys what is the origin of this dark energy I told you about? How does it change with time? It's going to look at the exoplanet census of the galaxy. It's going to allow for other astronomers to do general astrophysics, and it's going to have this really wide field of view that has 18 detectors. And I'm particularly really interested in that part because I'm a person who studies detectors. Now, here's an image that I showed in the beginning of this view of the Andromeda Galaxy. As you see from this cutout, that's the field of view of the Nancy Grace Roman Space Telescope, wide field instrument, and it's large. You can even see in comparison to the Hubble field how much larger it is. So there's going to be lots of exciting things that we can learn about our universe using this new telescope. Now, in my talk, I focused a lot about the light we get from the universe and how we learn about the universe through light. But we're finding ways to allow all people learn from light, not just people who have sight. Here, and you'll find these links later on the website, I showed that we have people who have taken data from the X-ray telescope, the Chanda telescope, around the center of our Milky Way galaxy and turned that data into sound so that you can actually listen to the center of our galaxy in X-ray using your ears. There are also groups, and I show one group here at the University of Learning that are also making Hubble data accessible. Tactile astronomy is taking images of the Hubble Space Telescope and making them tactile so that you can feel beautiful images of our universe taken from the Hubble Space Telescope. So hopefully I've shown you in this talk that we learn a lot about our universe just by looking up and looking and catching the light of the universe. Most of the light we're getting in the universe is coming from galaxies. And these galaxies, where stars are born and where we are born, light the path to where we come from, where we are, and where we're going. And so next time you have an opportunity to be outside, take a look outside and look at the stars and appreciate how special the light we get from stars is. And if you happen to be in a really dark location, get a little Finder Star Mapper app and try to find the Andromeda Galaxy, our nearest neighbor. It's really neat to look at through a telescope if you have an opportunity to do that as well. All right, thank you and have a good night.
Thank you so much, Dr. Mosby, for that fantastic talk and glimpse into your work. In Gregory's talk, he touched on dark energy and the ways he's able to study it through tools. Up next, we'll learn a little bit about dark matter and how theoretical physicists are studying it. We're pleased to be joined by Dr. Chanda Prescod-Weinstein. Chanda is an assistant professor of physics and core faculty member in women's studies at the University of New Hampshire. She's also a monthly columnist at New Scientist and a contributing columnist at Physics World. Using ideas from both physics and astronomy, Dr. Prescod-Weinstein responds to deep questions about how everything in the universe got to be the way it is. She is lead axion wrangler for the NASA Strobe X probe concept study. Chanda's first book will be released on March 9th, 2021, just a few weeks from now. Titled The Disordered Cosmos, A Journey into Dark Matter, Spacetime, and Dreams Deferred, the book takes a popular science approach and draws from her experience and knowledge as a Black woman theoretical physicist. Tonight, she's sharing a talk titled Finding Dark Matter. Here's Chanda.
So thank you for that kind introduction. I'm excited to be able to talk to you all today about finding dark matter. And I'm Chanda Prescod-Weinstein. I'm at the University of New Hampshire, and I'm coming to you from a very snowy environment. And I hope that you are all very cozy as you're watching this talk. So I'm going to talk to you about dark matter. I want to situate this in context. What I do is theoretical cosmology. In particular, I do particle cosmology. But the main thing is, what is cosmology? So cosmology is the area of physics and astronomy where we study the origins of space-time and pretty much everything inside of it, particularly on large scales in the late universe. So what you're looking at here on this slide is a timeline that goes from lots of question marks because we don't really know what happened at the beginning of our bubble of space-time, the space-time that we call our universe. And it goes all the way up to what we call the present. So obviously this is not to scale. It would be hard to put the entire universe on a slide to scale. And one of the things that I want to highlight for people is that there are different time periods that are important, and they're not evenly spaced. So this is a nonlinear map of what matters in the cosmological timeline, as we call it. So at 10 to the minus 43 seconds, the space-time seems to have expanded very quickly. This is the era of inflation that you may have heard, the inflationary universe. There's also a moment at about 300,000 to 400,000 years after whatever got all of this started, when you can see in this kind of drawing here that it looks like there's kind of like a particle stew or soup happening. And at about 300,000, somewhere between 300,000 and 400,000, the universe becomes transparent. And so instead of having this particle stew where light, if it's trying to go anywhere, tends to run into things, for the first time, light is able to travel freely through the universe. So this is called the cosmic microwave background radiation. And I'm going to talk about that more in a moment. So one way that I think about the work that I do is trying to figure out how all of these pieces of the timeline connect to each other. So based on the physics of what we know from this era of 10 to the minus 43 seconds, how do we get to an accurate description of everything that happened between then and the 300,000 years? And then how can we use the information that we can learn about this 300,000 year point to understand the exact evolution of galaxies? And therefore, really, in a lot of ways, you can think about this as we're trying to figure out how we get to us. Because we are part of what comes with galaxies evolving very, very clearly. So if a condensed matter theorist was giving you a talk, they would probably say that whatever they work on is the most exciting thing in the universe. But since this is my talk, I get to say that thinking about the cosmological timeline and all of the stuff inside of it is, these are the most exciting questions in the universe. So something that you won't see on this diagram, but is a pretty key question, is that it turns out that somewhere in here, and really we are still not sure when, something that we now call today the dark matter forms, and it actually becomes dominant in the process of going from this moment of transparency to the formation of stars and ultimately the formation of galaxies. That dark matter really shapes how structure formation occurs in the universe. That's what we call it when you make a galaxy, is it's the formation of structure. So one of the big open questions that's lurking but that you can't see on this diagram is, what is the dark matter? So one way of thinking about some of these questions to get a little more technical. So I highlighted for you on that last slide the 300,000 to 400,000 year point where the universe becomes transparent to light. So we can actually see the light that first started streaming at that point. And as I mentioned, it's called the cosmic microwave background radiation. So what you're looking at is a temperature map of the sky at about 2.73 degrees Kelvin. This was taken by the Planck telescope, which is a European Space Agency and also NASA project. And so I say it's a temperature map that's one temperature of about 2.73 degrees. You'll see that there are little color variations in this map, even though like if I put my mouse here and then I put my mouse here, you can't tell the difference between these spots. It looks the same basically no matter where I put the mouse. And if I put my mouse somewhere and then were to look around in a circle around that point, things would look about the same in all directions. So it's isotropic, it's homogeneous. These are two fundamental cosmological principles that on large scales, this is how space-time is. But you'll say, okay, yeah, kind of, but I see color variations. So these color variations are there to emphasize for us little fluctuations in the temperature. And when I say little, I mean 1 part in 10 to the 5. So a decimal point with several zeros after it, right? So these temperature variations are actually really informative for us because they actually tell us where there was a little bit more of density of matter, like atoms and dark matter, and where there was a little bit of an underdensity, so less matter or dark matter than average. So these are basically variations in the temperature from the average temperature. And these variations actually tell us about the beginnings of structure formation. So we can see this radiation now, and this radiation basically has the imprint of the beginning of galaxies on it, which is pretty exciting. So one way of thinking about the work that we do in theoretical cosmology, and in particular in relation to the dark matter problem that I'm going to talk to you about, is how do we get from this map of the entire sky with these temperature variations, these little temperature variations, to the cosmological objects that we see today. So what you're looking at here is Sloan Digital Sky Survey data. And it goes out pretty far out. And what you're seeing is the cosmic web. So there are lots of galaxies in here. So somehow those little fluctuations in temperature, those imprints are the beginnings, tiny little quantum fluctuations that will then translate into the formation of galaxies. And so we know that this happens. We have some like vague idea of how this happening, but we don't know in detail how to get from point A to point B. And it turns out that it's really important if you want to understand how you get from point A to point B. Where do particles come from? And how do those particles interact with each other? And ultimately, what is the majority of the matter made of, and what are those relationships? So before I get into detail of what is everything in the universe made of, I do just want to tell you that from the point of view of a particle physicist, one of the way that I'm more likely to think about this, if I'm thinking like a particle physicist, so I do both, so I wear both hats, is the astronomers will think about how you get from that cosmic microwave background radiation to that Sloan Digital Sky Survey data. A particle physicist is asking, where do particles come from? So first of all, maybe there are some deep questions there about quantum gravity. Are particles inextricably tied to the emergence of space-time in the very early universe at that 10 to the minus 43 second moment? I might slip at some point in this talk and refer to fields instead of particles. So I'll just say that you can think of particles as excitations of fields that are everywhere. So there's a field that has the potential for a particle to be produced, and then a particle is just an excitation of that field. So one way of kind of merging the two perspectives is to ask, how did fields get so excited that the excitation led to structure formation? So really cosmology brings a lot of different things together, which is why it's such an exciting field to be working in. So of course, the one of the ways that these things come together is that in cosmology, part of the question that we're asking is what is the universe made of? Um, so at this point in time, based on observations, we know that actually most of the matter energy content, so if we think about one of the lessons of Einstein's special relativity, E equals mc squared, that there is an equivalence between energy and matter. Most of the matter energy content in the universe is these two things, dark energy and dark matter, that which are basically like we call them dark energy and dark matter because we can't see them and we have no clue what they are. So really, dark is, for better or for worse, like our way of saying we're confused. If so, dark energy, which I'm not going to talk about today, but maybe you'll have someone else who's talking about it, or that's definitely something to ask for. Um, is something that we think is there because space-time is expanding, and that expansion, it turns out, is accelerating. And the only way to make that happen is to have something like a dark energy that's driving that acceleration. We think that that's the best model for it. In the case of dark matter, I'm going to explain to you in a second why we think that there's lots of dark matter. But one of the things that I want people to kind of sit with, one of the fantastical things that we've learned from doing work in cosmology, is that we tend to think of ourselves, like probably you've all heard, we are stardust. And it's true, we people are made of stardust. We are the remnants of older generations of stars. Um, and the heavy elements that exist on the earth are for the most part productions of either being produced in a star or in a supernova explosion or something like that. But actually, what we tend to think of as normal matter, all of the stuff that we can actually see in the universe, things that we can take pictures of with our fancy telescopes, all of that is a very small percentage of the matter energy content in the universe. So we people, we tend to think of ourselves as everyday stuff, but we're what is abnormal and extraordinary and unusual in the universe. So I think that that's something, I think the way that Carl Sagan put it is that we're actually just really precious um, because that we're actually rare. So I love sharing that with people, that we're what is unusual in the universe. So the universe is mostly made of stuff that's not at all like people. So okay, what is the dark matter? So the answer to that question is that we don't know. But here's the case for why we think it exists. So Vera Rubin, and an astronomer who just recently passed away a few years ago, and who was working in the 1960s and the 1970s, um, was talking with Kent Ford, who was an astronomer. He was also an instrumentalist who had built an instrument. And she was trying to figure out what were some interesting things that she could do with his instrument. And so she had the idea to look at how quickly stars were rotating in galaxies. And it's a basic Frosch physics problem that if you look at how quickly something is rotating, that you can also figure out how massive the thing is in total. So looking at the speed of stars in a galaxy can also give us a mass for that galaxy. Another way of getting a mass for the galaxy is by looking at how many stars there are and how much they're radiating, because actually, because the radiation in stars is coming from nuclear processes, it's actually the conversion of matter to energy. And so the amount of light that's being radiated from a star tells us how massive it is. So there are two different ways of measuring how much mass there is in a galaxy. And you would expect that they would match, that they would give you the same answer. And so what Vera Rubin found, and this was something that had been predicted in the 1930s, but no one had found evidence for it until Vera Rubin came along and did these observations, that the rotation curve, so on the vertical axis in this image, we have the velocity, and then we also have the on the horizontal, the distance from the center of the galaxy. What they observed was this green line. So this green line is the velocity as a function of the distance. And what you would expect, just based on the matter that we can see in the galaxy, would be this orange line. So there's a disconnect. So there are two ways of thinking about this. The most popular way is to think that we need more mass in the galaxy, more matter in the galaxy than what we can see. So the luminous matter in the galaxy isn't everything. But another way of thinking about it is that maybe we're interpreting our data incorrectly because we have the wrong theory of gravity. So there are people who work on a model called MOND, Modified Newtonian Dynamics. I would say it's a much more marginalized way of thinking about this problem, but I do want to acknowledge that that's one approach. But assuming that this is solvable with the dark matter, and there are lots of reasons to think that it is dark matter doesn't produce light, and that makes it very difficult for us to understand its properties, and it has become a very big mystery in cosmology. So the one thing that we do know is that it interacts significantly through gravity. So it seems to gravitationally interact just the way that all other matter interacts gravitationally. So it's attractive in the same way that humans are attracted to the Earth through gravity. Um, so I like to say it's only significant interaction is gravity, but it's possible that there are actually still other interactions through electromagnetism or through the strong and weak nuclear forces, and we have yet to detect those interactions. So that's an important thing to keep in mind, is that this is what we know. That doesn't mean it's everything, that it's all of the facts. Um, so those rotation curves that Vera Rubin first observed were the first key evidence for dark matter, but that doesn't actually mean that it's the only evidence that we have. So one of my favorite pieces of evidence for the dark matter is actually strong gravitational lensing. So here you can see, this is from the Hubble Ultra Deep Field, the Hubble Space Telescope Ultra Deep Field. And you can see that in this image, there are these weird like arc things, almost like making a circle around the galaxies in the center. So these are actually replicated images. And what is happening is that between these galaxies in the center and us, our telescope, there is so much matter, including dark matter, that space-time has been significantly curved. It's been bent. And that has caused space-time to act like a funhouse mirror. And so there are these replicated images of a galaxy because space-time is acting like a funhouse mirror. So one of the things that I like to point out to people is that dark matter actually isn't dark, because when we think about dark, we think about like uh, a dark blue, or I'm gonna paint my room black and put little like glow in the dark stars on it or something like that. And so we think of dark as somehow being associated with color, but actually dark matter doesn't have a color as far as we know. And the main thing is that it's luminous. So sometimes dark matter distorts space-time so that light travels unusual paths, but otherwise light travels right through it. So a better way to have intuition for the properties of dark matter is to really think that dark matter is invisible matter or clear matter. The reason that we call it dark matter is a little bit of a sociological reason. It's simply that was the name that was first given to it in the 1930s. And so we continue to stick with it. But is it actually the best descriptor? Not necessarily. So I would say either invisible matter or dark matter. Also, Nobel laureate P.G.E. Peoples in his most recent book calls it subluminal matter, which I like. So it's not as luminous as what we would consider to be everyday matter, but maybe it does emit some light, and we just haven't seen it yet. So what do we know about dark matter? We know that photons don't interact with it much. I've talked about that quite a bit. We also know from observations that it's slow moving, that it's not short-lived. It lives long enough to dominate the formation of galaxies. So actually galaxies are mostly made of dark matter. The part of galaxies that we can see is actually like just the interior, and then there's a whole halo around it. when we put these properties into computer simulations, they're consistent with hierarchical structure formation, that you go from the small to the big. So simulations and the data match on large scales, but it's still the case that I can tell you these properties of the dark matter, but I still can't write down an equation to describe it the way that I can write down an equation to describe an electron or a quark. And it turns out that no particle in the standard model of physics can be the dark matter. So this is what we call beyond standard model physics. So BSM, this is actually BSM is a technical term in physics. So and by the way, here on the right, I have an example of a simulation from the LSST collaboration. And you'll note that this looks not too unlike that Sloan Digital Sky Survey data that I was showing you earlier. So if you have the opportunity to rewind, you can actually go back and forth and compare the two. The great thing about not knowing what the dark matter is that this gives theoretical physicists something to do. So what you're looking at is a Venn diagram made by Tim Tate, who's the chair of the physics department at UC Irvine. And you can see there have been a lot of different theories of dark matter over the years. So almost everything on this diagram is a hypothetical particle. There are a couple of exceptions. I think there's one exception to this. So the one exception is primordial black holes. So since the discovery of gravitational waves a few years ago, we now know that there are enough stellar mass black holes that actually primordial black holes, so black holes that would have formed in the very early universe, are potential candidates for the dark matter. So we know that black holes exist. We're not super sure about primordial black holes and their formation, but they're the one thing on this Venn diagram that's kind of not like the others. So this is like the greatest Venn diagram of all time. For those of you who are maybe particle physics nerds like me, you might say, oh, but I thought neutrinos existed, so why are you saying it's a hypothetical particle? So sterile neutrinos are a hypothetical type of neutrino. They are not like the kind that we have observed. They're a very exciting dark matter candidate. I'm actually starting a research project on them. But the thing that I've spent most of my career thinking about for the last like 7 years anyway, is in this bubble in the lower left corner, axion-like particles, QCD axions, axion dark matter. So I'm just going to tell you a little bit about like what axions are and why. And I'm just going to warn you now, this is the slide with equations on it. I don't want you to panic. I love sharing with people what my work actually looks like, and it's okay if you don't understand it, but I hope you're a little bit intrigued by it. So where do axions come from? So in particle physics, the way that students are taught to write down the equation that describes the standard model of particle physics is that you write down every type of term that is allowed for the equation. And then you throw out all of the terms that disagree with known physics. So there's a term that can be added to the quantum chromodynamics Lagrangian. So this is the part of the standard model that governs quarks and gluons. If you want to learn more about quarks, you should pick up a copy of my book that's coming out on March 9th because it starts with a chapter called I Heart Quarks. So there's a term that we can write down, and it looks like this. You don't need to worry about what all of these things are. I just want you to remember that there is this theta in front of it. So it's the Greek letter theta. And this theta is just a constant, like it's a constant, like the gravitational constant. We can write this term down, and there's no theoretical reason to throw this term out. So no theoretical reason to throw this term out. The problem with having this term is that when we calculate its implications, it suggests that the neutron, which it has the name neutron because it should be a neutral particle with no charge distribution to it, the neutron gains what we call an electric dipole moment. So I know that some of my colleagues like to say that basically this suggests that the neutron has a shape that's inconsistent with everything we know about the neutron. So in theory, there's no reason to throw this term out, but experiment says the term should not be there. So this is a problem in the standard model. It's known as the strong CP problem because this term breaks what we call charge parity symmetry. So you'll be most familiar with charge parity symmetry because it's related to matter-antimatter symmetry. Um, so in the 1970s, Roberto Pecci and Helen Quinn proposed a solution for addressing this problem by upgrading theta so this theta to a field. So you remember that I said earlier that fields are like another way of talking about particles. So they made the theta dynamical. And in making it dynamical, what that means is that it can change. So it can go from having a non-zero value to having a value of 0. And so that is essentially the Pecci-Quinn mechanism, is that what they say is that they relax the term to 0 so that this term can be zeroed out. So of course, with this field, there is a particle associated with it, a scalar called the axion. So it was given the name the axion by Frank Wilczek, and it gains a potential via gluon interactions. It has a shift symmetry. These are mostly comments for the physics nerds in the audience. But it's a pretty exciting particle. And then part of what's exciting about it is that it not only could solve the strong CP problem in the standard model, but it also makes for a good dark matter candidate because there is a way of producing it in the early universe where it's cold. So cold is another way of saying it's not fast moving, it's not relativistic. It can have a small enough mass, so it's not going to be some giant object that's been floating around that we would have seen if it existed. So it has the properties that we need a dark matter candidate to have, and so that's pretty exciting. So in addition to the QCD axion that I was just talking to you about, one of the things that's very exciting about the axion is that there's actually an entire class of particles that are very similar to the axion. And some of them are well motivated by the quantum gravity theory, string theory. So in string theory, there are moduli, that's what they're called. And these moduli are essentially scalar particles that have shift symmetries. So that's why I mentioned those properties earlier. And they are much lighter in mass than what we would expect the QCD axion to have. So they are fundamentally different. One of the things that's really exciting about this is that when you think about what is the astrophysical phenomenology of these, what we call ultralight axions, so these string theory motivated axions, what you see is that you get galaxy scale fuzzy dark matter halos of axions. So you'll sometimes hear this term fuzzy dark matter. That's another way of talking about ultralight axions. So there's really exciting phenomenology that makes the axion particularly distinct as a dark matter particle. And I just want to credit that this diagram comes from a very nice paper by a team in Taiwan led by Xue. So one question that you might be asking at this point is, how do we find these particles? Like, is there a way to actually look for them, or are we just kind of constantly staring at the sky going, well, maybe it's an axion? And so there's an effect called the Primakov effect. And essentially, axions, even though their most significant interaction with everyday matter is through gravity, they also will interact with the electromagnetic field. So the axion dark matter experiment at the University of Washington has a microwave cavity that's about this big, maybe a little bit bigger, but nothing like, for example, the particle experiments that you see at the Large Hadron Collider. And there's an 8 Tesla magnetic field inside of it. And the idea basically is that the axion will interact with this magnetic field. So you see in this diagram, these arrows, the axion hits the magnetic field, and the interaction produces 2 photons. So photons are little particles of light, right? So axions can convert into detectable photons in the presence of a strong magnetic field. And this GA gamma gamma on here is just the strength of the coupling between the axion and the photon. So it's basically how strong you need the magnetic field to be, in some sense, is what that number G is going to govern. So we can look for axions through what are called direct detection experiments like ADMX, the axion dark matter experiment at the University of Washington. So here is a timeline and a diagram of the axion dark matter experiments generation 2 projected sensitivity. So I admit this diagram is now a couple of years out of date, but this will give you just a general perspective of, so again, that axion coupling, the G A gamma gamma on the vertical axis, and on the horizontal axis, the possible axion masses, because the axion theory doesn't tell us a priori what the mass should be. And basically, this is a very hard experiment to do. They are just slowly scanning through this parameter space, looking for evidence of an interaction between the axion and the magnetic field in their cavity. So is this the only way to look for axions through direct detection? No. So I just want to remind you all kind of like the big picture of where we started. We're trying to figure out how to get from this cosmic microwave background radiation. So we started with an astronomy problem, and then I started talking to you about particle detection. So does astronomy have something to say? Thankfully, the answer is yes. And I'm excited to be able to work really in on both sides. They were trying to figure out how to get from that cosmic microwave background radiation to the Sloan Digital Sky Survey. So to this very big image that we have of the cosmic web. And in between, we have this schematic picture of what an individual galaxy's ecosystem looks like. So as I mentioned, the visible part of a galaxy is actually like a very small part of the picture. And so actually what we expect is that each major galaxy, for example, the Milky Way, is going to live in a dark matter halo. And I should say this is not at all to scale, but each galaxy is going to live in a dark matter halo. So this is all like dark matter that we can't see. We have the spiral disk, which is like the visible part of the galaxy. And really, this is exactly how we expect our Milky Way to be. And then also there are actually going to be subhalos that are home to satellite galaxies. So our Milky Way has, I think the last time I checked, the Milky Way has upwards of 60 satellite galaxies. So there are lots of galaxies that are actually like kind of, so many of these are called dwarf galaxies. That are actually being hosted by a larger galaxy. And all of these are part of an ecosystem of dark matter halos and dark matter subhalos. So just to go back, we're trying to figure out how to get from this cosmic microwave background radiation picture, and somewhere in between that and the Sloan Digital Sky Survey data, we have the formation of these objects that basically comprise that Sloan Digital Sky Survey data. So one of the ways that we are going out and looking for evidence to give us a better understanding of, for example, if we look at that diagram of the halo with the galaxy in it, is if I know the mass of the halo, how many dwarf galaxies do I expect? How many subhalos do I expect? So this is a problem known as the galaxy halo connection. One of the foremost experts on this is actually in California, Risa Wexler, who's the director of the Cobley Institute for Particle Astrophysics and Cosmology at Stanford and at SLAC. One of the ways that we're going to best understand the galaxy halo connection is by studying galaxies more deeply. And one of the very exciting facilities that is being built right now in the Atacama Desert in Chile is the Vera C. Rubin Observatory. So you may recall that I mentioned that Vera Rubin was the person who found the first significant evidence for the existence of dark matter. So it's of course incredibly exciting to be able to work. I'm part of the collaboration on this observatory, on an observatory named after her, and to pursue questions about dark matter using this observatory. So this is a very exciting thing that's going to be happening over the next decade, where we will be collecting more information. And these questions about the galaxy halo connection can actually help us place constraints on different types of dark matter candidates. For example, is it the axion or is it the sterile neutrino? Because the galaxy halo connection data will be different the simulations will be different depending on which dark matter candidate we're using in our simulations. So comparing that with data is going to be really key for distinguishing between different types of dark matter candidates. I also like to make the case to people that high energy astrophysics, so X-ray astronomy and gamma ray astronomy, is actually part of the future of high energy physics. So they tend to be very different fields. But I really think that the dark matter problem is one of the key areas that brings the two fields together. So what you're looking at is a diagram that's very similar to the one I showed you for ADMX. So you have mass on the horizontal axis and the coupling between the axion and photons on the vertical axis. This is a diagram that shows the ability of different high energy astrophysics observatories like the Chandra X-ray Observatory, the Fermi X-ray Observatory, the proposed Strobex Observatory. So this was actually a diagram that was created by Manuel Meyer for what I call Team Strobex. This is the team that I lead for this proposed new NASA X-ray Observatory. And if you would like to look it up, you can look up the archive paper with this number, and you can read more about how we're planning to place constraints on axions using high energy astrophysics. So I really think Vera Rubin is going to be an optical observatory on the ground. Hopefully Strobex will be an X-ray observatory in the sky. Astrophysics still has a lot to tell us about axions. I think we're in a very exciting decade. I really hope that the 2020s and then even the 2030s, it's going to be a decade of dark matter and of searching for dark matter and better quantifying what we don't know. Because at the end of the day, doing science is about what we don't know. So if you liked what I talked about in this talk, I have to encourage you to go out and pre-order my book. And if you don't pre-order it, buy a copy after it comes out on March 9th. You can get it now pre-ordered at your favorite local bookstore. I'm particularly excited to be book touring at independent bookstores. And you can find all of that information if you just Google it. So thank you so much for going on this dark matter journey with me.